Welcome back to our channel. In the peaceful silence of space lies a discovery that raises a million questions. Imagine a region of space where the rules seem to have been rewritten and where a celestial anomaly suggests the existence of a cosmic giant, the black hole Gaia BH3. Black holes have long aroused the curiosity of both scientists and everyday life. These mysterious objects in the universe have such a strong attraction that even light cannot escape their grasp. Anchoring in the fabric of space-time, they affect the environment in subtle but profound ways. But how would such a discovery affect us only 2,000 light-years away? Could this silent neighbor affect our solar system, or does its presence expand the cosmic mysteries surrounding us? So we all know that deep in the universe, black holes exert such a strong gravitational pull that they bend the fabric of spacetime. These cosmic mysteries are not just points in space, but dynamic regions where gravity is so strong that the normal laws of physics have a hard time holding it together. The gravitational pull of a black hole is really strong. This causes spacetime to warp and light to delay. But its effect, powerful as it is limited by the vastness of the room. The idea that a black hole can simply travel through space eating stars and galaxies is a misconception often spread not by science but by sensationalism and movies. The fact is that the gravitational influence of black holes does not extend to infinity. On the contrary, their influence decreases sharply with distance. So even black holes relatively close to our solar system, such as Gaia BH3, do not pose an immediate threat. To understand this, we turn again to history, specifically to the history of Cygnus X-1, the first black hole. The story begins not only with a discovery, but also with a bold step into the world of astrophysics. It was the late 1960s, an era of intense debate between celestial research and scientists. Cygnus X-1 was first detected as a source of unusually strong X-rays by a sonic rocket launched in 1964. The source was not just another point of light in the night sky, but a source that emitted X-rays with an intensity that exceeded almost everything else in the sky. The ruse came to a head when two of the most brilliant minds of their time, Stephen Hawking and Kip Thorne, made a now famous bet. Thorne argued that Cygnus X-1 was a black hole, and Hawking disputed this, hoping that he would be wrong as part of his deep search to understand this cosmic phenomenon. This stroke symbolizes the scientific curiosity and somewhat playful competition that drives many scientific discoveries. Cygnus X-1 is part of an X-ray binary system consisting of a blue supergiant star believed to be a black hole formed from the stellar mass. The black hole's strong gravity pulls material away from its companion star, which spirals into the black hole, heating it to millions of degrees and emitting X-rays. These emissions allowed astronomers to study the properties of this mysterious object in more detail with instruments such as the Uhuru satellite launched in 1970, the first satellite designed specifically to study X-ray sources. The Uhuru satellite, the first space telescope, has provided convincing evidence that this object is indeed a black hole and the first of its kind. Cygnus X-1 has taught us a lot about the nature and behavior of black holes, especially how they interact with nearby matter. This is an important reference point for studying Gaia's BH3. Despite Gaia BH3's large mass, a whopping 33 solar masses, it remains a silent observer in space, mainly because it is at a significant distance from a star capable of providing material for an accretion disk. This distance indicates an absence of significant X-ray emission and a quiet presence, in stark contrast to the dynamic environment surrounding Cygnus X-1. While Cygnus X-1 is about 7,000 light-years from Earth, Gaia BH3 is closer, about 2,000 light-years away. Despite this proximity, Gaia BH3's passive nature and advanced knowledge of black hole mechanics give confidence in its safety. In our ongoing quest to understand the universe, the Gaia telescope has become a key player in the latest chapter of space exploration. Designed to map stars with unprecedented precision, it brought a new player to the cosmic arena, the massive black hole Gaia BH3, now the closest black hole to us. A mission to map more than 1 billion stars has provided a clearer picture of the galactic neighborhood than ever before. During this careful study, the telescope discovered an anomaly, a star whose motion could not be explained by celestial mechanics alone. This seemingly invisible star showed something massive that was hidden from view. And who is to blame? Gaia BH3, a previously unseen black hole lurking some 2,000 light-years away in the galactic halo. Gaia BH3 is not just a black hole, it is a cosmic colossus with a mass of 33 solar masses. This discovery places it among the most massive stellar mass black holes found in our galaxy. Its location in the galactic halo, a region inhabited by older stars and globular clusters, adds to its intrigue, suggesting a different origin or evolution than black holes found in the galactic disk. One of the most fascinating aspects of Gaia BH3 is its silence. Unlike the infamous black holes that make their presence known by gobbling up nearby matter and spewing X-rays, Gaia BH3 is eerily silent. The key to its silence lies in its isolation. The black hole's companion star orbits at a safe distance, too far away to break up and fall into the typical accretion spiral that forms an accretion disk. This distance prevents significant transfer of material, and as a result, Gaia BH3 lacks the usual signatures of black hole activity, such as the powerful jets and strong X-ray emission seen in systems such as Cygnus X. The recent discovery of Gaia BH3 not only expands the list of black holes we know, but also sheds light on the mysterious process of black hole formation from metal-poor stars. Metal-poor stars, composed mostly of hydrogen and helium with minor amounts of heavier elements, represent the early generation of the universe's stellar history. These stars lack the materials needed to synthesize heavy elements due to their low metal content, which greatly affects their life cycle and death. A star orbiting Gaia BH3 has been identified as metal-poor, an important clue to understanding its evolutionary path and the nature of its colossal companion black hole. Typically, the fate of a massive star involves a supernova explosion, heralding the death of the star and the birth of a neutron star or black hole. However, the scenario can be significantly different for metal-poor stars. The reduced opacity due to the lack of heavy elements allows the star to retain most of its mass, leading to a higher core density and direct collapse into a black hole after death without a spectacular supernova explosion. This direct collapse path suggests how Gaia's BH3 could form a significantly more massive black hole than those typically formed by more metal-rich progenitors. These direct observational data support broader theoretical models in astrophysics that predict a metal-poor environment that favors the formation of larger black holes. These results are very important because they can explain the existence of supermassive black holes that seem to have formed quickly in the early universe, overturning previous models of black hole growth that required longer time scales and multiple mergers. By studying Gaia BH3 and its stellar pattern, astronomers can gain valuable information about the early conditions of the universe, when stars were more common. This discovery not only links the past processes of star formation and death to the phenomena observed today, but also helps to close gaps in our understanding of the distribution and density of black holes in space. However, science does not stop. In a stunning fusion of artificial intelligence and astrophysics, researchers led by the California Institute of Technology have pushed the limits of black hole detection. This team successfully applied advanced artificial intelligence technology to visualize frequent flashes in 3 dimensions.